So 10.5 in your textbook, we're talking about transmission and reflection of waves. Yesterday you did an activity using a slinky and a rope or a string tied to the end of the slinky. And we talked about different things. We talked about waves and their reflection. We talked about waves and their interference. So a lot of the stuff that we're talking about today, you should think back to that activity from yesterday and say, yeah, I actually did see that with that little slinky activity. So you want to take down these notes here. It says, when waves strike a surface, the reflection of the wave, and of course with the slinky yesterday, you saw that when you sent a pulse or a wave down the slinky and someone else was holding it at the other end, then it bounced back, right? You saw that to happen. So waves do reflect off of hard surfaces. It depends upon the condition of the surface. So it depends upon the surface. So how a wave reflects, and if we're talking about a sound wave, it would reflect differently off a cement wall than it would off of a big curtain, right? Or a piece of foam or a mattress or something. So waves bounce off things differently depending on the condition or the type of the surface. And in this case, we're talking about if the surface is fixed, so that's someone holding firm on the end of the slinky from yesterday. The wave reflects in the inverted position. Did you guys see that in your activity yesterday? Anybody? Well, I know I saw some groups do it, and some of you did. You send a pulse down the right side along the floor, and it hits and it quickly flips to the left side and comes back, right? Or vice versa. You may have seen that with the pulse, okay? So inverted. So if we're talking about up and down, it reflects down here in the inverted position. So whichever way the pulse is oriented, when it hits the fixed end, it flips. Okay? If the surface is free to move, and I don't know if we did this in our activity because slinkies, it's a little tough for slinkies to be free because they coil right up. But if the surface is free to move, the wave reflects in the original upright position. And these are the diagrams here to, yeah, you should, recognize this from yesterday. And maybe if you were holding that little string, right, and you sent a pulse down there, sent a pulse down the slinky, and you were holding the string kind of, moved wildly. But any reflection that you would have seen probably came back on the same side. It would have been pretty small, but it would have came back on the same side. So if it's free to move, the reflected pulse is in the same upright position. Okay. So when we talk about this spring yesterday, the slinky and the yarn, the string, this is what we're talking about when we talk about waves exhibiting partial reflection. If the medium is different, so the medium is what the wave is traveling in. And our representation of that yesterday with that little activity was we had a slinky and then a piece of string. So let's just read here what this says here. Diagram 1 shows the transmission of a wave when traveling into a medium that is less dense. So traveling into a medium that is less dense. So that would represent, in this diagram would be represented by, this looks like it would be the slinky, right? It's thicker, it's heavier, and this is the string, or the yarn, pretty light, right? So in diagram 1, what's happening is if we had a pulse down the slinky, I don't know if you guys noticed, but a pulse coming down the slinky here would make the yarn move quite wildly. And your length of string was not very long, so this was tough for you guys to see it. Next time if I do this, I'll probably make that length of yarn, double the length so you can see it a bit more. But you had a pulse down the slinky, and then it hit that yarn, and the yarn just went wildly back and forth. I saw that in your activities there. So the velocity and the amplitude of the transmitted wave is increased. So the transmitted wave is the one that gets passed along. So the transmitted wave, I'll just maybe circle that in your notes, is this wave. Okay? That one. The transmitted wave. So here's the original wave. It hits the border of the medium and it gets transmitted or transferred. This is the transmitted wave. So if you think about a different example, let's say you have a really thick rope, right? You know those ropes that you guys work out with like this, you know? Maybe you have or a tow rope from a vehicle or something. You have a really thick rope, and if you had a little slinky tied to the end of that thing, and you got it, you just sent this big pulse down this rope. As soon as it hit the slinky, you can imagine the slinky would just go wild, right? And especially if it was under some pressure. So, if it goes into a lighter medium, the velocity, that is the speed. So notice that this arrow is about this long, and over here the arrow is longer. So that would represent the speed, okay? And then, of course, the amplitude is the height of the wave here. So you have sort of a smaller amplitude here, and then it's larger. So the transmitted wave. So velocity and amplitude is increased. Okay, so continuing on with number 1 here, the reflected wave, right? Okay, the reflected wave is over here, right? The reflected. Transmitted is on this side, reflected is on this side. We'll write that down. The reflected wave here is upright, so it's the same orientation there. This is upright, but has less amplitude. So reflected wave, upright, less amplitude, because energy is lost in transmission. So the bulk of this wave is transferred to this other medium, but there still would be some that would be reflected back. And notice that because this joint here, this boundary, because it moves, it acts like a free end, right? It moves up and down. And so the pulse here that's being sent would be reflected back in the same upright position. Because the string is it's quite a bit lighter, so it's like a free end in this reflection. If we look at diagram 2 here, shows the transmission of a wave when traveling into a medium that is more dense. So this would be like the yarn from yesterday, big pulse being sent down into the spring. Okay? The transmitted wave is slower, so you can think if it hits a thicker or more dense medium, it's going to go a little bit slower. So here's your original speed, and then here is the transmitted speed. The transmitted wave is a little slower and has less amplitude. So it's like it's got to work a little bit harder to go through the dense medium. So it's transferred all right, it's transmitted, but it's a little bit slower and a little bit smaller amplitude. There is a reflected wave as well, but remember, because it's a thicker medium, it sort of acts like a fixed end. And the reflected wave is inverted, like it would be if it was a fixed end. It's slower as well and also has less amplitude. So these diagrams are pretty important to memorize and to have a good visual of. So I'm going to just erase some of this stuff here now so that you can leave yours on, of course, but I'm just going to erase some of that. Okay, and I believe that these diagrams are right in your textbook as well. So if you have room in your desk, if you have your textbook open, check out what page that's on. Let's say here, when two or more waves act upon the same particles simultaneously, and so the particles would be, the particles on the string or that piece of, yarn that you had tied to the middle of the string, right? So that's the particles of the medium. When two or more waves act on the same particles simultaneously, the waves are said to interfere with each other. Now, if we stop right there, you could probably picture in your mind, you've all been to a lake, maybe some of you have been to the ocean, and if you imagine like a shoreline that's not completely flat, let's say there's a bit of a point or something, and you see, waves coming in one way and waves coming in at a slightly different angle, and what happens when they meet right? There's kind of some weird stuff that happens, right? So this wave is coming along, it looks fairly consistent, and then it starts to, it starts to do some crazy stuff. It interferes, and so there's some predictability with this interference, and that's what we're going to look at. There's a principle called the principle of superposition, and that's the predictability that I'm talking about. And it states, and you would have seen this yesterday in your Slinky activity as well, it states that the resulting wave, or the resultant wave, is the sum of all waves acting upon the particle. The sum of all waves. So, if you recall yesterday, let's just continue this diagram. Let's say these waves get really close together here, right? They're coming closer and closer. And what you would have noticed is that the wave, at the point where they interfere, right? This is what each wave would have looked like on their own. And what you would have noticed, it was very quick. And I kind of helped some of you through this because it was really hard to see. But when you got the wave coming at the same time and approximately the same size wave, at the very instant it interfered, did you see something like this? Like a big wave for a split second? Okay? Okay? Good answer. Anyways, I'm hoping you did anyways. But if you have one wave that's this size and another wave that's the same size, this principle says that the sum of them, so you have this size amplitude and then another this size amplitude, it should create a sum of an amplitude that is what the addition would be. So in two waves like this, when they collide, when they interfere, they will add up to the resulting wave. And that actually happens for every single wave. The other thing that you guys did was you guys sent a pulse that was sort of opposite amplitude, right? Amplitude here, positive, negative. And you sent them towards each other. And what would have happened there is that at one split instant, okay, they would have canceled each other out. So this one's a little bit tougher to draw, and this one would have been pretty tough to see. But at an instant, okay, so there's this wave right here, and this one up here, at the same instant they collide. If they were identical in amplitude but just opposite in direction, what would happen basically is you would have the particles would be basically wouldn't move. There would be at least one region here that wouldn't move. Technically, you would have something like this happening, and then it would be kind of really kind of convoluted here. But basically, there's lots of interference so that they cancel each other out. And if we're talking just about this one point right in the middle, this would not change its position at all as the waves passed. Everything else around would experience some violent movement here, but this one point right here is called the node, and it wouldn't move at all. So this one, like I say, if you took a video of this, and maybe next time I'll do this, I'll get you guys to take videos of this so you can slow it down and look at it. And maybe we'll look at a video here in a bit, but you would have seen that the waves that come in like this, right, at the exact instant they pass, there would be a point in the middle that wouldn't move at all, because they would be exactly canceling each other out. And actually, there would be an instant where everything like this, where the slinky would be straight, but it only would happen for a fraction of a second. So when I talk about sum, let's say this has a negative amplitude here, and this has the same positive amplitude, then they would add together to equal 0. And that's what we mean by sum. Okay? That's the principle of superposition. Question on that? Okay, so once again, constructive interference, waves combine to form a larger wave, like in this example right here. And destructive, they combine to at least partially cancel each other out. And we saw that with the pulses in yesterday's activity. Video, or you want to go into watch this video. It's Bozeman Science, and so here it is right here. I'll make this larger. And the part I want to focus on, it's a good video, the part I want to focus on is this standing wave. And I'll just play this out here right now. I'm just going to mute what he's saying for now. But as you watch this, the black wave is the resultant wave of the red and the blue as they pass. This is called a standing wave, but if I pause this at any point, what you can see is a couple things, is that the black wave is indeed the sum of the two waves. So if we have a small negative value for this red wave and a small negative value for this blue wave, the sum would be a larger negative value. Or over here, right here, the blue wave, the amplitude is 0 at this point. And the red wave amplitude is, let's say, a +1. Well, the resultant would be 1 plus 0. So that's why the part of the black wave is right on the red wave. So I'll just play this for another few minutes, and you can kind of see how there's constructive interference here and here, and destructive interference right here. And so he's just going over the sum of the waves here as well. So this is the activity that we're going to do. We're going to have two fairly random waves pictured, and then you're going to draw the resultant wave. Okay? So let me just introduce that for you. But I want you just to draw a wave like this, okay? And then another wave sort of like this. Okay? So just take a moment to try and replicate these two waves. This is sort of like a snapshot of what is happening. This is what's happening when these two waves, the green wave, it doesn't matter what direction at all is traveling, and the black wave, when they interfere with each other, so at a single snapshot in time, this is where they are. Now what we're going to do is we're going to draw, and I'm going to draw in red here, so a different color. I'm going to draw the resulting wave. Okay? Now how I want you to go about this is this. I want you to take a series of vertical points, okay, and these are going to be kind of like snapshots, and we're going to draw the resulting wave at these points. So watch how I do this. If we start over here, okay, this is at the very beginning, we really have it's 0, right? So our resulting wave at the very beginning is going to be 0. Why? Because there's no black wave over here, and the green wave would be 0 at this point. Over here, so again, if you look at it like algebra, right, this is about positive 0.5, right? You can see those lines there, positive 0.5. That's about half a square up, okay? And where's the black wave? Not even there. So guess where the resulting wave is going to be? The resulting wave at this point is going to be at 0.5 plus 0. And that's going to be 0.5. So we have the point right there. If there's only one wave involved, then the points are all on that wave. Over here now, okay, we have this happening. We have about 1.3 for the blue wave, or for the green wave, 1.3. And the black wave here is just starting to launch off 0. And so we're going to add, let's say, negative 0.1. Let's just say that that's maybe what the size of this wave is at this point. So everyone see what I'm doing? On this vertical position, just a random vertical position, I'm taking the sum of the two waves here. So that's 1.2, right? And so you go up 1.2, and here is the dot for the new wave. You see, it's like just you subtract this little negative part. So this is about, let's say this is about 1.3, I guess, the same as over there. So we've got 1.3 and the positive, right? And down here we have a negative about, let's say, negative 0.7. So I'm adding negative 0.7. Okay? And so this is going to result in a positive what? 0.6. And so that's where we go. We go from this vertical spot here, we go up 0.6. You see how that's working? It's a sum of the two waves. And we keep going here. I won't write out this one, but this is about 0.5 and negative 0.5. So what's that going to do when you add, I will write it, 0.5 plus negative 0.5, what do you get? 0. So guess what? The resulting point there, the wave is going to be right on the axis on 0. And over here it's 0 as well. So the resulting wave in red would be basically you would connect these points that you've drawn, and this would be the resulting wave. Okay. Whatever. Yeah. Okay. So then these are pretty much balanced off too, so you can just connect the points here. And that red wave then is the resultant wave. Okay? Everyone get that example? Straight line here. Okay? And let's have one wave like this. No whistling, please. One wave like this. And let's have another wave like that. Okay? So in this example here, we do the same thing. We just take random points, and I'm just going to, mark off just kind of these points right on the the vertical lines of my graph paper on my screen. So those are the points that I'm going to consider. I'm going to make dots on those, and the more points you make, the better your diagram would be. But let's just focus on these right now. So far right here, we only have the green wave, so the resultant wave is just going to be the green wave only. There's no black wave to add on to, right? At this point, though, this one right here, we have, that looks like about a 1.3. So let's say we've got 1.3, and we're adding another positive, maybe 0.2 there. Okay? And so here we have a resultant wave of positive 1.5. So this is an example where, we have to bring this above the wave. See? We have a positive wave, that's the 1.3, plus another positive part, 0.2, adds up to 1.5. Got it? Okay, just simple adding. It's adding integers. This one, okay, 1.3 again, and about 0.8. So what's 1.3 plus 0.8? Got about 2.1. So 1, 2.1, there's our resultant wave. Good with that? As we speed up here a little bit, this will be about 1.1, and because it's an intersection point, another 1.1. So this isn't one of my lines, but I thought just of good note. So 1.1 and 1.1 is 2.1. So the sum of these two waves over here and the sum of these two waves right here would be the exact same. Okay? And then this looks fairly symmetrical, so we could say, hey, we have 1.3 and 0.8 again, and so it's somewhere around the exact same spot here. Okay, over here we have about 1.3 and 0, so the resultant wave is 1.3. At this point right here, I have 1, 1.0, plus, now this, remember, it's below the line, so it's negative, so about negative 0.6 is about 0.4. Positive 0.04, so looking like that. Okay, the sum of the two. This one, 0.5, and then negative 0.9. So 0.5 plus negative 0.9 is going to be negative 0.4. Right? And so then, of course, with no second wave, we just along the wave like that. And so if we try our best to carefully connect the points, we see we have something like this as our resultant wave. Okay? This is a little exercise in math. That's all it is, adding integers.